a good reason for that, because nobody believed in quantum mechanics seriously before 1980, until there was a proof of Bell's theorem. Bell's theorem comes about because Bell wanted to prove that quantum mechanics was wrong. So he came up with this inequality and said that if the quantum interpretation is wrong, then experimental outcome should be in a certain manner. And if the quantum interpretation is correct, then we should be on different sides of the equality. Unfortunately, after he derived his theorem, experiments were conducted to prove his theorem one way or another. Either you should favor quantum interpretation or disfavor it. Okay? When you disfavor it, then this is different. Are you either true?
Yeah.
Okay. So if you disfavor quantum interpretation, then you will have the other side of the inequality in Bell's theorem. Quantum interpretation is essentially the interpretation that follows the Copenhagen school, led by Niels Bohr. Okay. In that school of interpretation, it is said that before you perform a measurement, a quantum state can be in a linear superposition of different states. Okay? So you might have a quantum state, you might be in a linear superposition of two states, for instance. And that you do not really know what state the quantum system is in until you perform the measurement. Okay? And after the measurement, then the quantum system collects one of these two states. Before you do the measurement, the quantum system is in a linear superposition of these two states. And that is something very difficult to accept for many people. If you want to relate this to something more macroscopic, say in our everyday life, say Mr. Zhang, he could sit on this chair or that chair. This would be the two states that he could have. Okay? In a quantum world, okay, he will be in the linear superposition of these two states, either on this chair or that chair. And you really never know which chair he's sitting on until you perform a measurement. And if you perform a measurement and found that it's on this chair, then he collects to the state that have him sitting on this chair. Okay, so quantum measurement is like that. And I liken that to angels and ghosts. I think all of us read ghost stories. We read stories about angels. Angels have the capability of being everywhere in this room. Okay? And angels have and ghosts have the capability of being on the two chairs simultaneously. You don't really know where you are until you pin the ghost or the angel down with the measurement. And quantum systems are of this nature. Okay? So because of this very peculiar nature of a quantum system, you can use this to encode information. And use this to do work for you. Okay? So out comes different things like quantum cryptography, quantum communication, the 3 QCs, okay, quantum computing. And quantum computing is very powerful because of quantum parallelism. Okay, so I can describe quantum parallelism in a very simple-minded manner. Say, if you have a Great Wall of China, you want to inspect the Great Wall of China. It has a hole. Some part of it is defective. If you were to use the classical method, you would send hundreds of workers to inspect the Great Wall of China and try to look for this hole. Okay? But if you are able to use quantum parallelism, you will create a quantum state of a soldier. Just one soldier who simultaneously can be everywhere along the Great Wall of China. Okay? So you send this soldier there, and just with one command, he can tell you where the hole is. And he can come back and tell you where the defect in the wall is. So this is roughly the idea of quantum parallelism. So you can get a particle to be simultaneously doing different tasks for you, like a ghost or an angel. You can get quantum computing to be a lot more powerful compared to classical computers. Okay, so this is roughly the idea of quantum parallelism, because of the fact that you can get a state to be a linear superposition of two states before you actually do the measurement or have the quantum system collapse to a definitive state. Okay? So in quantum cryptography, we have this no cloning theorem, and I'd like to go through what that is. Okay? Which means that you cannot clone a quantum state. Once you have prepared a quantum state, you cannot clone it. And let's see how this is the case. Say, all quantum systems can be derived by a time evolutionary operator, which is given by this operator. If you know the Hamiltonian of the quantum system, you can say that the quantum state will evolve according to time with this time evolution operator. So say if I have two states, ys2, okay, let me see if I have to, oh, here it is. Yeah, here's the example. Say if I have two states that I have prepared for a quantum system, or two quantum systems that are coherent with respect to each other. Okay, two quantum systems, system 1 and system 2, they're in quantum coherence with respect to each other, which means that the phase relationship between these two quantum systems is precise and exact, and they do not become incoherent. Okay, and that if I have a time evolution operator that can operate on one of the systems to change it so that it looks like the second system, I want to have this time evolution operator operating on system 2, so that after a certain time it becomes the same state as system 1. System 2. So this time evolution operator operates only on system 2. You have two quantum systems, 1 and 2, in quantum coherence with respect to each other. Okay? And let's assume that this is true. Such an operator is possible. And then I also can do the same thing if the quantum system is prepared in such a manner that system 1 is in state B instead of state A. Okay, then if I prepare such a thing, I should be able to time evolve system 2 so that it becomes like system 1 again. Okay, let's assume that this is possible. And let's prove that this will give rise to a contradiction. Okay? Let's assume that we have a state C that we would like to replicate in system 1, that is the linear superposition of the two previous states. State A plus state B. Okay. System 1 is now written as a linear superposition of two states, state A and state B, that we tried to clone previously. Then, if I apply the same time evolution operator, prepared with system 1 in an arbitrary state, and then system 2 is now in this state, and system 1 is in that linear superposition of states. Okay? So if I apply this to that, then I would have this been equal to 1 over root 2 by the principle of linearity of quantum system. I can multiply this out, and we'll have something that looks like this. System 2, system 1, plus the time evolution operator operating on system 2, system 1. Okay? So, after a certain time, okay, this system will become something like this. You can replicate the state A, you can replicate the state B, okay, but it definitely is not replicating the state C. Okay, so this is not equal to psi C2, psi C1. So if it had been able to do this, it would violate this principle of linear superposition. Okay, it would have violated the principle of linear superposition. So this is called a no cloning theorem, that you cannot clone a quantum state. Because if you clone a quantum state, you will violate the principle of linear superposition by that very simple example over there. Okay? Are there any questions regarding this? Yes?
Yeah, but what will be the phi C2 times the phi C1? It's like you said they're not equal. If there any like other term like exists there, which is what can make the two things.
Right. If you multiply this out, then you will have 4 terms. You have 4 terms, right? And then if you use the principle of linear superposition, you can only have 2 terms. So you cannot produce 2 terms or 4 terms from 2 terms. Okay? So it's not possible to clone this thing so that it looks something like that. If the previous 2 cloning experiments are correct. This assumes that you can clone. This assumes that you can clone. If you can clone, you arrive at this contradiction. So then it implies that this must be wrong, this must be wrong. Okay, this cannot be done. If it can be done, then you arrive at a contradiction. Okay? That's a very good question. Yes? Psi S is a state that you start out with. Okay, you state system 2, you can start out with this state, then time evolve it so that it looks like the state of system 1. Okay? If you assume that you can do that experiment to get that to happen. Okay? Okay? Another very important concept in quantum information is the concept of entangled states. Entangled states are states that you find is only true for quantum systems. You cannot find this having this classical analog. Okay? So you can generate photon entangled states, for instance. And photons are very much a particle that behaves like a quantum particle. A quantum particle is a particle that can have a linear superposition of 2 states. And experiments have confirmed that a photon actually has that property. That it can be thought of as a quantum particle which is able to be decomposed into linear superposition of states. And before you do the measurement on the particle, you do not know what state it actually is. So we can see that why photons can have that kind of property, and you can start with phonons. Phonons are essentially, when we study the linear atomic chain problem, we have a whole bunch of particles hooked up together with some coupling between them. And each of these, if we regard as a quantum particle, they oscillate like a quantum particle, like a simple harmonic oscillator. Then they can propagate a pulse of energy along the linear atomic chain, and that pulse of energy also behaves like a quantum particle because the origin of that pulse of energy is actually due to these quantum particles You can think of photons as being due to electron-positron pairs. In vacuum, lurking in vacuum, and then as it polarized vacuum with electric field, give rise to a pulse of energy that propagates in vacuum. That pulse of energy propagates at the speed of light. Okay? And that pulse of energy very much behaves like a quantum particle. It can be broken into linear superposition of two states. And one way to break a photon into two states is to use the polarizing, the fact that if a photon is vertically polarized, okay, it is actually due to some oscillation of quantum particle. You can think of this as being the linear superposition of a particle polarized in this direction plus a particle polarized in that direction. Okay, so a vertically polarized particle can be thought of as the particle polarized in the plus 45 degrees or minus 45 degrees direction if you want to. Okay, this is plus 45 degrees, this is minus 45 degrees. These two are orthogonal to each other. We know that this polarization, a particle oscillating in this direction, can be broken up into a particle oscillating in this direction, plus particle oscillating in that direction. And you can think of this as being something like that, like the 45 degree state plus 1 over root 2 minus 45 degree state. Okay, and this is usually called the vertical polarized state. So in this manner, you find that photons behave like a quantum particle. It is equally likely to be found in this state or that state. And if you were to do experiments to study this property, you will find that half of the time will be polarized in this direction and half of the time will be polarized in that direction. Which means that if you have a vertically polarized photon, you send it through a polarizer. Say if the polarizer is polarized at 45 degrees. Okay? And then you find that the half of the time this photon will pass through this particle. The other half of the time, the photon is in this other state, which is orthogonal to this polarizer, and half of the time it will not pass through this polarizer. Okay? That is the property of the photon being polarized. This is vertical, this is 45 degrees. The minus 45 degrees is orthogonal to this other direction, and only half the time the photon will go through the polarizer. This is the polarizer. Okay? So we have to think in this manner that the photon is a quantum particle. And one photon by itself can behave like a quantum particle. Then you can have this kind of quantum interpretation for what a photon is. Are there any questions so far? So we saw that we quantize electromagnetic field, and once we quantize it, we can treat electric field as an operator. And electric field can be linear superposition of plane waves propagating in all different k directions, okay, with this prefactor, the volume epsilon naught. And then a polarization. The polarization can be horizontal or vertical. It can also be right-hand circularly polarized or left-hand circularly polarized. So this can represent different kind of polarization for the photons. And then it can be described by this annihilation operator, and then the other attracting factor is associated with the electric field that satisfies Maxwell's equation. Okay, we actually derived this in class before, that the photon is described by that state, linear superposition of plane wave states. And they have to be linear superposition of plane wave state because this field operator has to also satisfy Maxwell's equation. So Maxwell's equation still holds true for even quantum nature of electromagnetic field. And then we can describe what state we are in by using direct notation. For instance, if I have only one of this plane wave state, I would say that the photon is in this state with a vertical polarization. Say if I have only one term in this with only one plane wave. I say that the photon is in this state using the Fock state notation. Okay? But usually if you just have one plane wave state, that is not physical because this photon is not localized. It spans all of space. So this is only the ideal case of a photon propagating with one plane wave state. And more practically, you want to think of a photon as superposition of different plane wave states. Say if you have only a vertically polarized photon that actually leaves an atomic experiment, and then there is a pulse of energy that leaves the photon. This pulse of energy has to be localized in space. And if you just have one plane wave state, this photon cannot be localized. So if you superpose a bunch of plane waves, you can get this photon to be localized. So this is a more physical picture of what a photon is. Okay? But then these k vectors are going to be very close to each other because at very high frequencies, to make a wave packet, you just need a few k vectors in the vicinity of the original k vector, and you can have this forming a wave packet. And the wave packet will have most of its energy concentrated around the carrier frequency of this wave packet, if you want to think of it that way. And then there will be a frequency associated with it too, which is sort of, this wave packet will have a whole multitude of frequencies because it's not purely monochromatic. This is purely monochromatic, but that is unphysical. So in order to make a wave packet, you need a certain bandwidth of signal, and hence this has different frequencies for different states, okay, in order for you to make this packet. So when you think about h bar omega quantization, you actually have h bar omega k over sum of different k's. But all these k's are very close to each other. Okay, so this can be approximately represented by the mean h bar of omega naught. Okay, this one is the mean of this, and then you can think of this packet of energy having a mean frequency. Okay, this, if you fully expand it, you might have a spectrum that looks something like this, and omega mean might be close to the center of that thing over. And you can think of photons as such. And so we will not write a photon in this manner because this is too cumbersome. We use this notation to mean a photon. Meaning that if you write a photon with this notation, it means that there's a cluster of frequencies around it that makes it into a wave packet. Okay? We will not use this long notation. And when we write something like this, it just means something like that. Okay? So I can give, like if I have two photons, one going in A, in this direction, one zipping away at the speed of light in that direction, another photon zipping away at the speed of light in that direction. I can represent the quantum state of this photon emission as being something like this, that psi AB of two photons together has been just 1 Ka B. Okay, let's assume that both of them are vertically polarized for state A, for this thing that is traveling in this direction, okay, plus multiplied by 1 Kb B state T. Okay, I can write the total state of this quantum system as a product state, and assume that these two states are coherent with respect to each other. They came from the same source. They are coherent with respect to each other. I can write the quantum state of the photon emission process in this manner. Are there any questions so far? So as a shorthand notation, instead of writing this with the Fock state like this, I would often write this as just V1 and V2 to indicate that A is 1, B is 2. I have two photons. And then write the state of these photons. one being vertically polarized, the other one is also vertically polarized. I will use this product state to represent the two photons. Okay? Okay, then there are entangled states. Entangled states are very peculiar to quantum mechanics, states of quantum mechanics. Those are states that cannot be factorized as the product of these two states. These two states are not entangled in the sense that you can already write this as a product of two states. There are many states called the Bell states. That are entangled. An example of them are for photon system is that if you have this whole bunch of them, if you have a horizontal polarized photon in system 1 and then horizontally polarized photon in system 2 plus vertically polarized photon in system 1 and vertically polarized in system 2. They cannot be written as psi 1 times psi 2. No way that you can factorize this system. This quantum state is called an entangled state. Okay? And then there are many of this example. Another one is that you have two photons propagating in different directions, and then just a negative sign actually. This one has just a negative sign. D1, D2. Okay, this is the second Gauss state. And then you have the other one that involves horizontal and polarized state. Okay, plus 1, 2. It will be equal to horizontal polarized 1, vertically polarized for photon 2, plus then vertically polarized for photon 1, horizontal polarized for photon 2. And then you can have the minus state that we change this to the minus sign. So there are 4 of these states, okay? Plus, minus states. And those are all entangled states because they cannot be written in such a manner. So the peculiarity of the entangled state is that since they cannot be written as this factor, that means that these states are always in the linear superposition of two states. Let's take the first Bell state as an example. They are always the quantum system of the aggregate system. If this aggregate system is such, and if these two photons are correlated, okay, the quantum system is in a linear superposition of these two states, either horizontally polarized for both photons or vertically polarized for both photons. And we do not know what state the two photons are. It's either in this state or that state. Okay? So if you perform a measurement on one of the photons and find that it is horizontally polarized, then immediately you know that the aggregate quantum system is in this quantum state. Immediately you know that the other photon is zipping away at the speed of light in the other direction is also horizontally polarized. Okay? And the same thing applies here. If you measure one of the photons, you find that it is vertically polarized. It must be in this state because it was in the linear superposition of these two states. And then immediately you know that the other photon is also vertically polarized. The same applies to that kind of thing. Yes?
I'm just curious, why did this is super brief? I mean, you can go something faster.
Right, so this is faster than the speed of light. So Einstein doesn't like it. A lot of people don't like it. Which means that you can know immediately what the other photon is after you perform a measurement of one of the two photons. So information is traveling faster than the speed of light. Well, so people don't believe this kind of thing for a long time. But then if you look at Bell's experiment, Bell's theorem, and experiments to confirm Bell's theorem. Agrees with quantum interpretation, that you do not know what the state of the system is until you do the measurement. And once you do the measurement, you immediately know what the state of the system is. And that can imply for two photons that are zipping far apart and traveling the speed of light. And I read somewhere that people did experiment in, was it Geneva or somewhere? They sent two photons on an optical fiber and they found that they are correlated, entangled, even when they're miles apart. Okay, so they found this kind of entanglement in many experiments. It's hard to believe, but it's spooky. Einstein calls it spooky. Okay. So information can zip right away across the universe and tell you that the other photon. Maybe somebody will come up with a new theory in the future that save all this spookiness. I don't know, but this is what we have at this point. Okay, because of this spookiness, we have quantum information. Or maybe no, maybe we just have to live with this spookiness of quantum mechanics. So, there is a simple example where I illustrate how you can create quantum states that are as such. Say if you have a atom that generates two photons, one goes in this direction and the other one goes in that direction. Okay. Then if it is, this one is right-hand circularly polarized, it turns out that there's no angular momentum to start with this. Okay, if this is right-hand circularly polarized. The others is also right-hand circularly polarized because you define right-hand circularly polarized depending on if you're in the area of optics or microwave, that the thing spins in this way, and in the other direction it spins in that way, so they're counter spinning in different directions if you look at the spinning of the photon. So together they have no angular momentum. Okay, together you have no angular momentum because they're actually spinning in opposite direction as they propagate. Okay, so such a quantum state can be, for instance, described by such a possibility. Right-hand circularly polarized for photon 1, and then photon 2 is also right-hand circularly polarized. Plus left-hand circularly polarized for photon 1, left-hand circularly polarized for photon 2. And then we know that right-hand circularly polarization state is a linear superposition of horizontal polarized state. Okay, plus vertical polarized state. I may need the factor of root 2 there, but let me ignore that for the time being. So if you have horizontal for photon 2, it will be the same thing. Linear superposition of horizontal polarized plus vertical polarization. The same thing for L, okay? And then the same thing for L2. And then you can plug that in. After some algebra, you can see that this quantum state can also be written as 1 over root 2 horizontal polarized 2. So it's just an illustration that this kind of state can be generated in experiments. Okay, this kind of Bell states can be generated in experiments. If you do experiments, you can actually generate two photons that are entangled with respect to each other, so that if you were to measure the polarization of one of the states, one of the two photons, you immediately know the polarization of the other photon. So, because this is very peculiar nature of photons, we can use photons for quantum communication and quantum encryption. And let's see how this is done. Let's discuss a very simple case. The fact that the photon can be vertically polarized and horizontally polarized, those are the linear superposition of two states. And then the photon is actually behaving like a ghost and angel. It can either be horizontally polarized or vertically polarized and so on. Okay? So this is the famous Alice and Bob. I guess you must have heard of this story before, Alice and Bob story. And they are trying to communicate with respect to each other using photons. But these photons are quantum particles. Okay? So they want to send photons to each other. The photons are either vertically polarized or horizontally polarized. Okay? So when it's vertically polarized, it's one state. When it's horizontally polarized, it is a zero state. So they can send digital information to each other using photons. Okay? So they can send a whole bunch of photons with different polarizations, and then can send ones and zeros to each other. And let's see how they can make their communication channel secure because of the quantum nature of photons.